Hi everybody, in this video we are going to continue to talk about reactions. More specifically, we are going to talk about the factors that affect the rate of a reaction. The first factor comes down to surface area, or the area of the surface that is available to react. So in this example, a sugar cube will dissolve slowly because there is a low surface area. Meanwhile, something like powdered sugar will dissolve much more quickly because there's more surface area when you crush up things. And to prove the point, I will do an example where I have a cube, each with a side length of 1, and we know that the surface area of the cube will be 6 times the area of each side, which is 1, and that makes a surface area of 6. Now what if we split this cube into 8 equal cubes? So perhaps something that looks like that. So there are 8 cubes there, and each of these tiny cubes has dimensions that are half of the original, and there are 8 of them. So the new surface area for one cube is going to be 6 times the area of one side, which is 1/2 times 1/2, or 1/4. And we have 8 of these, so each cube has this surface area, but we have 8 cubes, so the total surface area will now be 12. So notice how by crushing this cube into 8 identical cubes, we effectively just multiplied the surface area by 2. So in general, by crushing things into many pieces, we get a larger surface area. So what about the state of reactants? How does the state of reactants affect the rate of the reaction? Well, you could think of a solid as a cube, and you could think of liquids and gases as powdered sugar, since in a solid, of course, we have a rigid structure, but for liquids and gases, you have free moving particles that move around each other, and these are typically separated from each other, and they flow around, and that's why the surface area of solids is generally lower than the surface area of liquids and gases. And thus, if you have a gas, then you will have a greater reaction rate than if you had a solid, for example. So what's another factor that changes the rate of a reaction? Well, we learned in previous videos that the reactant concentrations can affect the rate of a reaction, because the higher the concentration, the higher the rate. And this does not apply to zero order substances, since for zero order substances, the rate is unrelated to concentration. Now the third factor affecting rate is going to be temperature. A higher temperature means particles collide more frequently and with more energy, which typically increases the reaction rate. The fourth thing is the presence of catalysts. Catalysts are substances that speed up reactions and are not consumed. So these are 4 main factors that affect the rate of a reaction. And before we continue, kinetics is the branch of chemistry involving the rates of reactions. So that's just something cool to know, because that's actually the name of Unit 9. So now let's move on to something called activation energy. The activation energy is the minimum amount of energy that molecules must possess for the collision of molecules to be effective collisions that result in a reaction. Activation energy is typically found in kilojoules per mole. What are some factors that impact the rate constant K? Well, you have to ask yourself 3 things, and these 3 things will determine how large or how little the K is. What fraction of collisions and reactions occur in the right orientation? This is known as the Steric Factor P. So if there are a greater fraction of collisions that are in the right orientation, then you will have a higher rate constant. Now the second point says, how often do collisions occur? And this is known as the collision frequency Z. So of course, the more often molecules collide, the more likely they are going to react, which means that the rate constant is going to increase, since the rate will increase if more stuff reacts. Number 3, what fraction of molecules have enough energy to react? Or, in other words, what fraction of molecules have an energy equal to or greater than the activation energy EA? This is symbolized by the letter F. So, the more fraction of molecules that have enough energy, the more likely that they are going to react, which increases the rate constant, since if more molecules react because they have enough energy, then the rate will go up. So now we can combine these three factors into one equation, saying that K is equal to P times Z times F. We won't go into exactly the numbers behind this, but just know that if P, Z, or F go up, then K will also go up as well. Now, apparently, a scientist found out that F is equal to e to the negative of the activation energy over R times T. So, before we go on, we can substitute P times Z and note that Z is the number of collisions and P is a fraction of those collisions in the right orientation. And if you multiply these two together, you essentially get the number of collisions in the right orientation, so that's denoted by the letter A, which is the number of collisions in the right orientation. And using the equation above, you can see that by moving things around, F is equal to K over P times Z. And we know that P times Z is A, so F is equal to K over A. Now we could substitute K over A here, and we could say that K over A is equal to e to the negative of the activation energy over RT. And multiplying both sides by A, we get this equation, K is equal to capital A times e to the negative of the activation energy over RT. This is known as the Arrhenius Equation. So we can actually go a step further and do some math so that we can find the rate constant at different temperatures. Now this should remind you of the Clausius-Clapeyron equation, which was discussed in the videos about vapor pressure, or more specifically video 7.1. So we are going to play around with the Arrhenius equation. We are going to take the natural log of both sides, do some math, do some simplification, and some log tricks, and we get that the ln of the rate constant is equal to the ln of A minus the activation energy over RT. And let's just shift this up and let's put two different conditions where we have K2 and T2 and K1 and T1. So this is a system of equations, and I will subtract these two equations from each other going downwards. So you get this minus this is equal to this minus this. And notice how the natural log of A cancels out because ln of A minus ln of A is 0. So simplifying this, we can get the natural log of K2 over K1 is equal to the negative of the activation energy over R times 1 over T2 minus 1 over T1. So notice how I factored this out of that. So this equation is very useful because it allows us to find the rate constants at different temperatures. And let's review our units. So EA is in joules per mole or kilojoules per mole. R is our gas constant. It is going to be 8.31 joules per mole times Kelvin, or 8.31 times 10 to the negative 3 kilojoules per mole times Kelvin. And depending on what you want to find, if you want to find it in joules, then you gotta use 8.31. If you want to find EA in kilojoules, then you should be using 8.31 times 10 to the negative 3, because you want the kilojoules or the joules to match during the math process. Now temperature is in Kelvin, and K is a rate constant. And if you're not given the order of the reaction, I would not worry so much about the rate constant's units. Now before we continue, note that if a reaction increases by a factor, the rate constant gets multiplied by the same factor. So this is assuming that the concentrations are constant. So if I have a rate and it's equal to K times A, and let's just say that the rate is multiplied by 2. If the concentration of A stays constant, then this must mean that our rate constant K must have been multiplied by 2. Now let's use the Arrhenius equation in a practice question. The rate constant doubles when the temperature increases from 20 degrees Celsius to 30 degrees Celsius. Find the percentage by which the rate constant increases going from 30 degrees Celsius to 40 degrees Celsius. So we are given a lot of information, and let's just deal with the first half. So it says that the rate constant doubles when the temperature increases from 20 degrees to 30 degrees Celsius. So this must mean that K2, or the rate constant after, is twice that of K1. So we could write an equation. K2 is twice that of K1. So I could substitute it into this cool equation that we derived in the previous slide, and we see that the ln of 2K1 over K1 is equal to the negative of the activation energy over 8.31, so our answer will be in joules. And note that the two temperatures are going to be 30 degrees Celsius for K2 and 20 degrees Celsius for K1, so T2 must be 30 degrees Celsius, since that's when it's K2, or the condition afterwards. And we need it in Kelvin, so we simply add 273. So 30 plus 273 is going to be 303. Now, we have to subtract by 1 over T1, and T1 is going to be 293 Kelvin. And doing the math, I converted the fractions into decimals to keep track of sig figs, and we know that 2 is an exact number since it says that it doubles. And when it says that it doubles, I am assuming that it doubles exactly because, I don't know, they don't indicate how many sig figs are in here, so I'm just going to assume that 2 is an exact number. So doing the math, I get that the ln of 2 is equal to all this, and then we do some more math. We multiply both sides by 8.31 to cancel this out. And on the left-hand side, we are left with 5.76 is equal to the negative of EA times negative 0.000113, and the underline there is to keep track of sig figs. And then doing the math, we get that EA is equal to 5.1 times 10 to the 4th joules per mole. Now we can use this information to figure out the percentage by which the rate constant increases going from 30 to 40 degrees Celsius. So we have new conditions. K1 is at 30 degrees Celsius, or at 303 Kelvin, and K2 is going to be at 40 degrees Celsius, or 313 Kelvin. Now we just simply plug it in again, and this time we don't know what K2 and K1 are. We want to find the ratio between K2 and K1 to figure out how much times greater is K2 than K1. So I know what EA is. It's this, but negated because there's a negative sign there. And we divide it by 8.31 once again. And we go 1 over T2 minus 1 over T1. And doing the math, converting things to decimals, keeping track of sig figs, and doing some math, doing some simplification, we get that the ln of K2 over K1 is equal to 0.646, and the underline there is to keep track of sig figs. And we take the anti-log, and we figure out that K2 over K1 is equal to e to the 0.646, and when you take the anti-log, the number of decimal places becomes the number of sig figs. So 2 decimal places, 2 sig figs in our answer. So it looks like K2 over K1 is 1.9. So K2 is 1.9 times as large as K1, or in other words, K2 is 90% more than K1. Therefore, the rate constant increases by 90% going from 30 degrees Celsius to 40 degrees Celsius. So pretty cool. We tackled a challenging problem and we did it. Now, let's talk about the Arrhenius equation in terms of the Maxwell-Boltzmann distribution again, since we did talk about this in gases, but now we are applying it into this chapter. So the Arrhenius equation tells us that increasing the temperature increases the rate constant and thus the rate. If you increase the T, the number of collisions increase, which increases the number of collisions in the right orientation. And in addition, by increasing T, more particles have enough energy to overcome the activation energy barrier. So over here, we have a Maxwell-Boltzmann distribution once again. And as you can see, molecules at higher temperatures have, on average, more energy, of course, so the peak of the molecular distribution shifts to the right. And this is because the peak of the curve could be thought of as the average or median energy that the particles have. So higher average kinetic energy, which is temperature by the way, that means that there is a higher average energy, or the peak will shift to the right. Now, molecules at a higher temperature also have a wider variety of energies that they can adapt, so the curve flattens. And you can think of it this way. At lower temperatures, most molecules are forced to adapt a low variety of energies, making the frequency much higher in those ranges and making the peak higher at lower temperatures, as shown here. But as you increase the temperature, it flattens out because the molecules have more options in terms of what energies they can adapt. And notice how the peak shifts to the right as temperature goes up. So let's now talk about something else. You can think of the area under the curve as the amount of particles. So the area under this curve is telling you how many particles there are. So it seems like in this region of energy, there are more particles than in this region, for example, not only because the peak is lower here than here, but also because the area under the curve is higher here than here. And they're both essentially the same concept, so you could think of the amount of particles as where the curve is, or the area under the curve. So I like to think of it as the area under the curve because, as you will see, it will make things easier. So I have the activation energy marked on the graph, so let's just say that right here is the activation energy. Particles having a higher energy can overcome this minimum energy barrier and potentially react if they have the right orientation. As you increase the temperature, a larger proportion of molecules overcome this activation energy barrier, which increases the reaction rate. So, in other words, if you look on this graph, at 100 Kelvin, notice how the area under the curve past the activation energy is kind of low. It's like over here. And this tells you that not many particles can overcome the activation energy at 100 Kelvin because, as you notice, the area is small and the frequency of these particles are low in these areas too. So what about at a higher temperature, such as 500 Kelvin? Well, notice how now more particles are at the region that passes this activation energy barrier, and all these particles, so I'll shade the area as the particles, all these particles have enough energy to overcome this activation energy and react. And if you go at even higher temperatures, such as 1000 Kelvin, you notice how most of the particles will have enough energy to overcome the activation energy barrier and react. So as you increase temperature, there's more area to the right of the barrier, and thus more particles can react at higher temperatures, which increases the rate. So let's talk about what a catalyst does. A catalyst, so there's no S there, a catalyst speeds up reactions by lowering the activation energy. It does this by offering alternative pathways that the chemicals can travel to get from reactants to products. These pathways have a lower activation energy. So, as you can see on this graph, this is the activation energy normally, and the blue line is the activation energy with a catalyst. Notice how it's lower. So, with the catalyst, a larger fraction of molecules have enough energy to react because the activation energy threshold is shifted to the left. It's as if the reaction lowered its standards and let lower energy molecules, once not having enough energy to react, to now react. So as you can see, for the old activation energy, only this many particles could react, which is not a lot, so the reaction rate is pretty slow. But by using a catalyst, notice how more particles are to the right of the activation energy barrier, and because of that, more particles can react, and the reaction rate actually increases with this catalyst. So catalysts increase the rate of reactions. So as I just mentioned, catalysts are not consumed in the net reaction, and we will go into further detail in the next video. Now you might be wondering, what types of catalysts are there? Well, we can look at a reaction such as the decomposition of H2O2 or hydrogen peroxide into water and oxygen gas. And this process is pretty slow at room temperature. So how can we speed this up? Well, with catalysts, of course. So we have catalase, which is found in potatoes, and catalase can speed up the decomposition of H2O2. So if you put a potato in some hydrogen peroxide solution, you will see a lot of bubbles starting to form because it will speed up and catalyze the reaction. Now, manganese 4 oxide or manganese dioxide is also a catalyst, and it's found as a black powder. Now, potassium iodide is also a catalyst. It's found as a yellow solution. Now, a fun fact is that some catalysts can increase the rate constant by a factor of 10 to the 12. That's a lot, by the way. Now, let's look at some metal catalysts that are used in the industry. We have iron, platinum, palladium, and etc. Now, we have biological catalysts, and these are catalysts that are found in our body, and they are typically made of proteins. And these catalysts are called enzymes. Enzymes can help us break down glucose into energy, for example. So in the very first step of glycolysis, which is a reaction that is required to convert glucose into energy, glucose is transformed into glucose 6-phosphate by adding a phosphate via ATP, and the catalyst, or the enzyme to be more specific, is something called hexokinase, and as you can see, the phosphate is added to the sugar. Now I want to talk about one last thing. It is called a reaction coordinate diagram. This tells us the energy pathway from reactant to product. So as we can see, the reactants start down here, and they have to increase to this much energy before transforming into the products. So this energy barrier, or this minimum amount of energy that is required before the reactants can start transforming into products, is known as the activation energy. So this energy difference from the energy of the reactants to the peak is known as the activation energy. And you might notice this delta H. So the difference in energy between the reactants and products is known as the delta H, or the change in enthalpy. And in this case, since products have a higher energy than reactants, the delta H is positive, and this reaction is endothermic. So that's all I wanted to do for this video. Have a nice day, everybody.